All right, guys, brand new unit, big unit too, all about circles. And we're going to start out this chapter with this lesson on circles and circumference. A lot of this stuff will be reviewed, but you may learn a few new things here. We're just going to focus mainly on talking about parts of circles and then solve some problems using circumference. We do have some vocabulary here, some of which may be new, some of which may be old. But let's start out with our fundamental definition of a circle. Now, in the past, some of you have asked me, isn't a circle just a polygon with an infinite number of sides? Or maybe a regular polygon with an infinite number of sides? And that's not quite an accurate definition of a circle. Technically, a circle is the set of all points that are in the same plane that are equidistant from some given point, which happens to be the center of the circle. And so for that reason, that's kind of why it's more precise to say it's a set of all points, because it doesn't really have sides like a polygon does. And in our circles, we have radii, which are line segments that have one endpoint at the center of the circle and one endpoint on the circle. We can also draw chords in circles, which are line segments that have both of their endpoints are on the circle. And a diameter is actually a type of a chord. It happens to be the chord. It has both its endpoints on the circle, and it passes through the center of the circle. We're going to talk about concentric circles. Concentric circles are coplanar circles that have the same center. So you might have a smaller circle inside a larger circle. Concentric circles are what you would think of if you throw a rock in a pond and you see the ripples form. Getting bigger and bigger. All of those ripples would represent concentric circles. Circumference. Circumference is, you can think of this as perimeter of a circle, right? We talk about perimeter polygons. Circles are special, so we give them a special name, and we call it circumference, just the distance around the outside of the circle. And pi is our special number that we've talked about a lot. It happens to be the ratio of a circle's circumference to its diameter. And it's a special number because for every single circle on the planet, no matter how big or how small it is, they all have this same ratio. That's what makes it special. Now I'm just introducing inscribed polygon and circumscribed circles here, even though we're going to use them more in future lessons. But an inscribed polygon is a polygon with all of its vertices on the circle. So I'll just give you a quick example. If we have a circle here and I drew a triangle and the vertices were all on the circle, I would say that that triangle is inscribed. And you could inscribe any kind of polygon, a pentagon, a hexagon, whatnot, and it would be considered inscribed as long as all of its vertices are on the circle. And therefore, we would say a circumscribed circle is a circle that contains all of the vertices of a given polygon. So we would say this circle is circumscribed about this triangle. Or we would say this triangle is inscribed inside this circle. All right, here's a visual to give you a little better idea of our main segments in circles that we're going to be talking about. A radius. And in this particular example here, we've got CE and CF and CD that are all radii of this circle. And it should be noted that, in the past when we've done proofs, we've sometimes drawn auxiliary lines. In this circle, even though there isn't a line segment drawn from C to B, I know the distance from C to B is the same as the distance from C to F or C to D or C to E. Because remember, a radius is just any segment that connects the center of the circle to a point on the circle. So I could draw an auxiliary line CB and call it a radius. I could draw an auxiliary line called CA and call it a radius. Now, a chord, remember, is a line segment with both of its endpoints on the circle. Here we have two chords. We've got chord AB and we've got chord EF. Okay, they both have their endpoints on the circle. EF is a special chord because it happens to pass through the center of the circle. And so EF is a diameter here. And you'll notice that every diameter consists of two collinear radii. I could say EC and CF are radii that happen to be collinear. They happen to share the same line. And when we refer to circles, we use a symbol. We use this symbol to refer to a circle. And we would name this circle by the point at its center. So we would call this circle C. Just in the same way that we would refer to triangles, like triangle ABC, we refer to the vertices. For a circle, we refer to the center point, and we use that symbol, circle C. All right, let's look at an example. Here, could we name this circle? Okay, so we're going to call this circle by the point that is at its center. So we would call this circle C. That would be how you would name it. Could we identify a radius? Well, I see two here. I could say that segment EC or segment CF. Those are both radii. Could we name a chord? I see two chords here. Remember, a chord is a segment that has its endpoints on the circle. So I could say segment AB is a chord. And I could say segment EF is also a chord. Okay. Could I name a diameter? I only see one diameter in this circle, and we would say that is EF. Okay. And note, EF happens to be both a chord and a diameter. It is a special type of a chord, the one that passes through the center. We call that a diameter. All right, let's try one more of these. How would we name this circle? Well, we'd call this circle R because that's the point at the center of the circle. Could we identify a radius? I actually see four here. I see ER, RD, RF, and RB. All of those are radii. I see three chords here. Could we name a chord? I see BF, that's a chord. I see EF, that's a chord because it has its endpoints on the circle. And we also have BD. And two of those three chords are diameters. EF happens to be a diameter because it passes through the center. And BD is also a diameter because it passes through the center. All right, how would we name this circle? I would call this circle P because that's the name of the point that represents the center. Could we identify a radius? I see three radii here. I would say OP is a radius. I would say LP is a radius. And I would say PN is a radius. Okay. Could we name a chord? I see 1, 2, 3, 4 chords. I see LM, right? I see MN. I see NO as a chord. And I see LN. Don't forget, just because it's a diameter. Diameter is a type of a chord. And could we name a diameter? I only see one diameter in this sketch that's drawn, and we would call that diameter LN. Okay, important concept, the relationship between radius and diameter. The radius in any given circle is going to be half the measure of the diameter, or you can say the diameter is going to be twice the measure of the radius. This makes sense because if a diameter is that chord that passes through the center, then it has to consist of, like we mentioned earlier, it has to consist of two collinear radii. And segment addition postulate tells us that if we add those two together, we're going to get this longer segment, which would be our diameter. So you can say radius is diameter over 2, or radius equals 1/2 times the diameter, or you could say the diameter equals 2 times the radius. All right, could we use that idea, the relationship between radii and diameters, to figure out if WX is 31 centimeters, could we find the length of MS? Okay, well, if this here is 31 centimeters and it's a diameter, MS looks like a radius, so it should be half of that. So this should be 15.5 centimeters. Notice, WS is a radius, so it's 15.5 centimeters, but every single radius in the circle will also be 15.5 centimeters. Try another one like that. If you want to pause the video and try this before I do it, that's a good idea. Here they're telling us that QA is 28 centimeters. Could we find the length of BT? Well, QA is what type of segment? That is our diameter, right? And if that's 28 centimeters, then how long is a radius in this circle? For instance, QT would be half of that, would be 14 centimeters. And that means that every other radius in the circle would also be 14 centimeters, because don't forget that fundamental definition of a circle. It is the locus of all points that are equidistant from some other point, which is the center of the circle. That means every radius in the circle is going to have the same measure. All right, so here's some properties of circle pairs that we can conclude from our definition of circles and what we just looked at in terms of the relationship between diameters and radii. Two circles are congruent if and only if they have congruent radii. So in this example here, if AB is congruent to CD, if they told us that, if I knew that information, then I could conclude that circle B is congruent to circle C. So if two circles have congruent radii, then they're congruent. It's as simple as that. A lot easier than proving triangles congruent. Another thing that's interesting is that all circles are similar. So in this example here, circle B is similar to circle C. I don't need to know any other information. A lot simpler than proving triangles similar. All I need to know is that this is a circle and that's a circle. And I know they're similar. I know they're proportional to one another. And the last thing that we're going to look at is concentric circles. Concentric circles are coplanar circles that share the same center. So here we have two circles that both have their center at F. And so it can be a little tricky naming these circles, because we said earlier, well, we would write that as circle F, but which one are we talking about? So here we would say we have a circle F with radius EF and circle F with radius FD are concentric circles. So that's how you would refer to them, so you can be clear as to which one you're referring to. Okay, here's a good problem. This is a nice little puzzle. The diameter of circle E is 24 inches. The diameter of circle H is 16 inches. And this segment FG is 4 inches. How long is EH? I'm just going to highlight that. That's what we're after. We want to know the length of this segment right here. Okay. And what information do they give us? The diameter of circle E is 24 inches. And I don't know if you can see this, but EG represents a radius in this circle. So if the diameter is 24 inches, what is this radius right here? EG would be half of that, right? This would be 12 inches. Good. And they tell us the diameter of circle H is 16 inches. So that's the diameter all the way across. And it looks like HF here. It's going to draw this guy in. Looks like HF is a radius of this circle. So if the diameter is 16 inches, the radius would be half of that, would be 8 inches. Good. And they also tell us that FG, this segment in here, is 4 inches. Okay, how long is EH? Well, if you want, probably the easiest way to do this is to break this down, because we've got these two segments that overlap. To make it less confusing, how long is segment EF? If we just look at this part of the circle, well, 12 minus 4 gives me 8. So on the top here, I'm going to write the length of each segment that's not overlapping. Good. And then let's look at this other circle here. If this radius is 8 and this segment is 4, then what's the length of this segment GH? 8 minus 4 leaves me with 4 inches. Okay. And now what I can do is just look at those top segments, those non-overlapping segments, and I can say that EF is going to equal the sum of 8 plus 4 plus 4. It's going to give me 16 inches. Good. These are neat little puzzles. Don't forget to label them and highlight them, and do whatever you got to do to keep things straight, especially when the information starts overlapping and getting confusing. Break it down into what you know. Keep it as simple as possible. Okay, let's try another problem like that. And if you want, go ahead and pause the video here and try this one on your own before I do it. The diameter of circle L is 18 centimeters, this guy right here. The diameter of circle K is 9 centimeters, and the diameter of circle H is 4 centimeters. How long is JL? JL, I'm just going to highlight that. That's what we're after. Okay. Let's see, what do they give us that we could add to our sketch here that would be relevant and helpful? If the diameter of circle L is 18 centimeters, then I'd like to mark this right here, this radius of circle L. This could be helpful. If the diameter is 18, then the radius would be 9, half of that. Okay. And they tell us that the diameter of circle K is 9 centimeters. So if this is 9 centimeters, then KL, for instance, would be half of that. It would be 4.5 centimeters. Good, that could be helpful. And then I could also say that this segment, maybe I'll just mark it right here. That segment right there is also 4.5 centimeters. Okay. And they tell us a little bit about circle H. Diameter is 4 centimeters. That means how long is HJ? That'd be a radius. That's half of 4 centimeters. This is 2 centimeters. Okay. And they want us to find this here. Okay. Well, I'm going to go ahead and I'm just going to, on the top of this segment JL, I'm going to write these non-overlapping distances, 4.5 centimeters. And here, if HJ is 2 centimeters and HK is 4.5 centimeters, then JK would be 4.5 minus 2. There's 2.5 centimeters left over there. Okay, so now I can see that JL is going to equal the sum of these two segments, 2.5 plus 4.5. So we'll get JL equals 7 centimeters. Good. You may have noticed another way you could tackle that is you could say here I've got 9 centimeters. And this JL is everything on this diameter except for this segment. So I could say 9 minus 2 gives me 7. Another way you could slice it. All right, circumference. And as we mentioned earlier, circumference is the distance around a circle. So it's analogous to perimeter in a polygon, right? And if you've got a circle with a diameter D or a radius R, the circumference is going to be the diameter times pi, or 2 times the radius times pi. Okay, so these are two good things to remember. Now I tell you guys, math is not about memorization. There shouldn't be too many things that you memorize. Once you're done with your times tables, everything else should be as conceptual as possible. But every now and then we have something that we want to remember that we've really got to kind of store away. This is one of them. Circumference equals pi times the diameter. Or circumference equals 2 times pi times the radius. Circumference equals 2 pi r. And of course, if you only remember one of these, you can always figure out the other one. All right, let's see what Dave's up to today. Dave found a bunch of crop circles in his buckwheat field. The largest of the 3 circles had a radius of 35 feet. Could we find its circumference? Okay. When you get a problem like this, I like to just write down what I know. The largest of these 3 circles had a radius of 35. That's r equals 35 feet. Okay. And now we had 2 formulas there for circumference. One of them involved the radius. That would probably be the easiest one to use. Circumference equals 2 pi r. Okay, so I'm just going to go ahead and plug in what I know. Circumference equals 2 times pi times 35. Okay? And don't forget, pi is dessert. Save it for last. Don't grab your calculator and multiply that pi in. Sometimes you don't even want to do that. Sometimes you want to have an exact answer, which means leave it in terms of pi. So I'm going to say 2 times 35 is 70 pi feet. Okay, if they ask for an exact answer, that's what they want. 70 pi feet. Now, you could go ahead now at this point and multiply by pi if you want, and because pi is a decimal that goes on forever, you ultimately have to round your answer. And that's why we make that distinction that this would be an inexact answer, 219.9. So the circumference is approximately 219.9 feet if you wanted to put it in decimal. Of course, if you're talking to someone and you're trying to relate to them how long something is or how big something is, you do ultimately want to take this last step. Because if you tell someone that just go walk out there 70 pi feet, they're going to look at you like you have two heads. So sometimes it's appropriate to do that. All right, while foraging for mushrooms, Dave found a large white pine tree. He was so impressed with the size of the tree, he measured it by wrapping a rope around the trunk. When he measured the length of the rope, it was 17 feet long. What was the diameter of the tree? Okay, so what is this asking? They want to know the diameter. What are they giving us here? What does the length of that rope represent? He wrapped it around the tree. So doesn't that represent the circumference? Can't we say the circumference is 17 feet? And if I know the circumference, could I work backwards and find the diameter? Circumference equals 17 feet equals pi times the diameter, right? Could I solve that for D? Well, if 17 equals pi times the diameter, I could divide both sides by pi, okay? And we could say that the diameter equals 17 over pi feet. And again, if you wanted to get someone to understand approximately what that represents, well, then you'd want to go ahead and divide by pi. 17 divided by pi. And we're going to get the diameter is approximately 5.4 feet. That's a pretty impressive tree when you think about it. It's about 5.4 feet across. That's a big tree. All right, let's look at another example here. Oh my goodness, what's this? Huh. Look at that. All right, could we find the diameter and the radius of a circle to the nearest hundredth if the circumference of the circle is 75 feet? This is a lot like Dave's problem with the tree, right? This time they're giving us the circumference. The circumference of this circle is 75 feet. C equals 75. And they want us to find the diameter and the radius. Okay, well, I could find the diameter and then just divide that by 2 to get the radius, right? So I could say 75 equals pi times the diameter. And in order to solve that for D, to get D by itself, I want to undo this multiplication by pi and divide by pi, right? So I would get our diameter is approximately equal to, let's go ahead and divide that, 75 divided by pi, and I get 23.873. I'm going to round that to, as they ask, the nearest hundredth. So 23.87 feet. And that means my radius, while I've still got that in my calculator, I'm just going to go ahead and divide that by 2 to get the radius, because the radius is half the diameter. And I get that my radius is going to be approximately 11.94 feet if I'm rounding them both to the nearest hundredth. Good. All right, here's an interesting problem. Could we find the exact circumference of circle P? And of course, the answer is absolutely not. You can't do that because there's missing information, right? Yeah, there's an important piece of information that was left off of this problem. It turns out that ON, this distance here, ON, equals 4 times the square root of 2 centimeters. Okay, now we can solve it. So if this guy here, ON, is 4 square roots of 2 centimeters, how could I find the exact circumference of circle P? Well, if I'm looking for circumference, I need to know the radius or I need to know the diameter. I got to know one of those two things if I'm going to be able to find the circumference. Can I find radius or diameter from this information? Hopefully you zeroed right in on the fact that this is a right angle. That helps us out. And something else that's going on here. This triangle OPN, hopefully you remember from our chapter on trigonometry that this is one of our special right triangles. How do I recognize that as one of our special right triangles? Well, what can you tell me about the relationship between OP and PN? Those are both radii of this circle, and therefore we know all radii in the same circle are congruent, right? And that means this is an isosceles right triangle. That means this is our 45, 45, 90 triangle, right? And hopefully you remember the relationship between the legs and the hypotenuse in one of those special right triangles, right? If you didn't, you could say, well, I'll call this R, and that means this is also R. And you can run through your Pythagorean theorem if you want to. You can say R squared plus R squared equals 4 squared roots of 2 squared. But if you remember the shortcut from our trigonometry unit, you remember that I multiply a leg by the square root of 2 to get the hypotenuse. So R times the square root of 2 gives me the hypotenuse, 4 times the square root of 2. Or maybe you remember I can divide the hypotenuse by the square root of 2 to get a leg. You can see here, we can go ahead and divide both sides by the square root of 2 to solve for the radius. And conveniently, we get square roots of 2 canceling. We get R equals 4. Okay, now that I know R equals 4, can I find the exact circumference of circle P? Circumference equals, what was the one in terms of R? There was 2 of them. Circumference equals 2 pi R, right? So we get circumference equals 2 times pi times the radius of 4. And if they want it as, I should have put my units on there, if they want it as an exact answer, that means leave it in terms of pi. Don't forget, pi is dessert. Save it for last. So circumference equals 2 times 4 is 8 pi centimeters. And that's an exact answer. Good. All right, one last example, guys, and then I will wish you good luck on the homework. Here they tell us that LM is 10. Could we find the exact circumference of this circle P? So this segment here is 10 units long. And, well, I'm going to need to know either D or R. I got to know one of those if I'm going to find the circumference, right? In this particular problem, looks like maybe we can find R pretty easily. If PL and PM are radii of this circle, that means these guys are congruent to one another. And that makes this my special right triangle. Right? This will be my 45, 45, 90 triangle. Okay, and in that I know if that's R and that's R, I know the hypotenuse always equals a radius times the square root of 2. So radius times the square root of 2 equals 10. And to solve that for R, I can divide both sides by the square root of 2. Square root of 2, I get R equals 10 over the square root of 2. Now, we know we'll have to rationalize the denominator there at some point, right? But maybe we can just save that for the last step. To find the circumference, knowing the radius, that's circumference equals 2 pi R. Let's go ahead and plug in what we know for R. Circumference equals 2 times pi times 10 over the square root of 2. Okay, now remember, pi is dessert, save it for last. So we get circumference equals 2 times 10 is 20 over the square root of 2 times pi. Now would be a good time to go ahead and rationalize that denominator. Remember, we don't leave radicals in the denominator. So what do I multiply this by to rationalize the denominator? I can multiply anything by 1 and not change its value. In what form? There's an infinite number of ways to multiply by 1. How about we multiply by 1 in this form? Square root of 2 over the square root of 2. right? So I get circumference equals 20 times the square root of 2 times pi. Don't forget that pi, bring it along for the ride. Over, what's the square root of 2 times the square root of 2? Well, that's just 2. Good. And we could further simplify this by seeing that we could divide both top and bottom by 2 here, and we would get circumference equals 10 square roots of 2 times pi. Good. And that's an exact answer. All right. Hope you found this helpful, guys. Good luck on the homework.